Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 2 on solving square root equations. Now basically what we're going to be doing is solving equations that have square roots in them. And it's really cool because this should be a natural extension to all of our equation solving work that we've done so far throughout the years, really. So let's jump right into it and solve some rather simple square root equations. Solving by inverses. Equations involving square roots arise in a variety of contexts, both applied and purely mathematical. As always, the key to solving these equations lies in the applications of inverse operations. The key inverse relationship in these equations is that between taking a square root and squaring. So what we're going to do is we're going to start off in exercise number 1, real easy, and we're just going to kind of build it up. Exercise number 1. Solve each of the following square root equations, which are arranged from less to more complex. Check each equation. All right, well, the simplest of them all, letter A, the square root of x is equal to 7. Now that's the kind of equation that you really should be able to solve literally by just thinking about it, right? Because this equation is saying what number, when I take its square root, is equal to 7, and of course that number is equal to 49. Well, how can you apply inverse operations to get that 49 so you don't have to solve by inspection? Well, the inverse of the square root is the squaring operation. So, if I'm going to actually figure out what my answer is without having to kind of like just think about it, I square both sides. Anytime I square a square root, I just get whatever is underneath it, and I get 49. Now, I realize it says check each equation, in which case I'll get square root of 49 is equal to 7 and 7 equals 7. So that's great, but that one's almost a little bit silly, right? Now, something like letter B, where we have the square root of x minus 3 is equal to 5, that's a little more complicated, but at least I can think order of operations, right? So what's happening to x? I'm subtracting 3, then I'm taking the square root. So to undo that, I'm going to square, and then I'm going to add 3 to both sides. So let's jump into that. All right, here we go. We're going to take this, square both sides. That's going to leave me with x minus 3 is equal to 25. And then, of course, I'm going to add 3 to both sides. And I'm going to get x equals 28. Now, one thing I'd like to review right at this moment is how we can use our graphing calculators to actually check whether or not something is a solution to an equation. So, for instance, in this second equation, which is a little bit more complicated, if I wanted to check to see whether or not x equals 28 was a solution to this equation, all right, one way to do that very easily is to take 28 and use the store command and put 28 in for x. All right. Once I've done that, I can literally then type out my equation. I can type in the square root of x minus 3 is equal to 5, right? And when I do that, of course, what I'm asking it is, if x is 28, then is the square root of x minus 3 equal to 5? And when I hit enter, I get true. Now let's just say I had a mental hiccup, right? And I did something where I had x minus 3 equals 25, and maybe I subtracted 3 from both sides, and I got x is equal to 22, right? Let's say I did that. So instead, I was like, oh, let me put 22, store it in x, and then typed in the square root of x minus 3 is equal to 5, it would tell me false, right? In other words, right, oh, hey, 22 doesn't make this a true statement, and therefore it is not a solution to the equation. I would highly advise using that to check equations, especially in something like what we're doing today. All right, that being said, let's get back into it. Why don't you go ahead and try to solve letter C on your own? All right, yet again, let's take a look at what we have here. Thinking about what's happened with x, all right, we have the square root of 2x minus 1 is equal to 4. So I've taken x, I've multiplied it by 2, I've subtracted 1, and then I've taken the square root. I'm going to undo that by squaring, right? I'm going to square first, then I'm going to add 1, and then I'm going to divide by 2. Remember, we're always doing the inverse operations in the opposite order in which they occurred. Therefore, I take this original equation, I square both sides, and I get 2x minus 1 is equal to 16. And at that point, it's kind of a piece of cake, right? I add 1 to both sides, and I get 2x is equal to 17. And I divide both sides by 2, and I get x is equal to 17 halves, or if you like decimals better, you could get 8.5, right? Either one of these would be a fine answer, or 8.5 if you wanted it that way, that would be fine. And again, it's just a piece of cake, right? I'm not going to do this on every one of them, but it's like really seriously easy to do something like this now. 17 halves, store that in x, then ask the question, is the square root of 2x minus 1 equal to 4? And true, right? So I know I've gotten this problem right based on the fact that that makes that a true statement. It's one of the great, beautiful things about modern graphing calculators is that it is very easy to check most answers to your equations without having to back substitute them in and see if the left-hand side's equal to the right-hand side. All right, now let's take a look at D, E, and F and see how they're a little bit more complicated. Let's check out D. Here we have 3 times the square root of x minus 4 is equal to 20. All right, let's talk about order of operations. Now, I look at x and what's happened. I've taken its square root, then I've multiplied by 3, then I've subtracted 4, and I've gotten 20. To undo that in the opposite order, I'm going to need to add 4, then divide by 3, and then square, right? So, I really have to think order of operations here, but as long as I've kind of worked through that, I get 3 times root x is equal to 24. Divide both sides by 3, I get root x is equal to 8. Square both sides, and I get x is equal to 64. All right, really, really simple as long as I can work through those order of operations. What I'd like you to do now is pause the video and try to work through both letter E and letter F, and then we'll go through both of them. All right, let's talk about letter E. We've got 2 times the square root of x plus 5 plus 7 is equal to 13. So I think about order of operations. I've taken x, I've added 5, then I've taken the square root, then I've multiplied by 2, then I add 7. So I'm going to subtract 7, I'm going to divide by 2, I'm going to square, and then I'm going to subtract 5. Literally, I can just lay out my equation solving steps right like that. So first things first, let's subtract 7. That's going to give me 2 times the square root of x plus 5 is equal to 6. Let's divide by 2. That's going to give me the square root of x plus 5 is equal to 3. Now we'll square it. That's going to give me x plus 5 is equal to 9. Great. Now let me subtract 5 from both sides, and I'll get x is equal to 4. Awesome. Simple enough. Let's try letter F, which is the most complicated, and let's walk through it before we do anything. I've got 5 times the square root of 3x minus 2 minus 4 equals 36. So watch. I've taken x, I've multiplied it by 3, I've subtracted 2, I've taken the square root, I've multiplied by 5, and then I've subtracted 4. So I'm going to add 4, I'm going to divide by 5, I'm going to square both sides, I'm going to add 2, and then I'm going to divide by 3. Right? All I have to do is think about the order of operations that's been done to x, and then undo them with inverses in the opposite order. So let's do this beast, right? I'm going to add 4 to both sides. That's going to give me 5 times the square root of 3x minus 2 is equal to 40. I'm going to divide both sides by 5. That's going to give me the square root of 3x minus 2 is equal to 8. I'm going to square both sides. That's going to give me 3x minus 2 is equal to 64. Whoops, I should put the squaring there as well. I'm going to add 2 to both sides. That's going to give me 3x is equal to 66. And then I'm going to divide by 3 on both sides. And I'm going to just tuck it in here. I'm going to get x is equal to 22. All right. I mean, this looks like a terribly complicated equation. And yet, as long as you're able to look at the left-hand side of the equation and think about what has been done to the variable x, then you can just undo it one step at a time. Now, inverses work fantastically to solve all sorts of equations, ones with square roots in them and ones without square roots in them, as long as the x shows up only once. All right. As soon as x shows up more than once, then we have to start doing algebraic manipulation and bringing in other techniques like the zero product law, factoring, things like that. But if x only shows up once, then you should be able to identify all the operations that were done to x and then undo them using inverses in the opposite order in which they had originally been done. Wow, that was wordy. Let's take a look at a multiple choice problem. Here we go. Exercise number 2. Which of the following is the solution to 3 times the square root of x divided by 2 equals 15? Awesome. Well, pause the video now and see if you can figure out what the correct solution is. All right, well, honestly, some of you might have said, you know what I'm going to do is I'm just going to use the store command and see which one of these 4 make this true. Very legitimate, by the way, very legitimate. And I think, even though some math teachers would say, well, that's not the point, I would claim, well, that's still actually some good math, right? And that's showing that you understand that the solution to an equation is a value that makes the equation true. But regardless, let's go old-fashioned here. I've taken x, I've divided it by 2, I've taken the square root, and I've multiplied by 3. I'm going to undo all of that by dividing by 3, squaring, and then multiplying by 2. Let's do that. All right. So first things first, let's divide both sides by 3. That's going to cancel and leave me with root x divided by 2 is equal to 5. I'll square both sides. That'll leave me with x divided by 2 is equal to 25. And then I'll multiply both sides by 2. And that will leave me with x equals 50, or choice 3. Now, square root equations can be a little bit tricky, all right? Because they can have what are called extraneous solutions, and we're going to talk about this a lot more on the back side of the sheet. Sometimes the solution to a square root equation can produce an answer that's incorrect, especially when negatives are involved. So let's look at a very simple example of that first, and then the back side of the sheet we're really going to kind of dig in and look at it a little bit more closely. So, exercise number 3. Solve the equation square root of x plus 1 equals -4. Then check your answer and explain why it is not a solution. All right, well, go ahead and do exactly what we just did. It's actually a relatively simple equation. Let me first maybe write it down so that we really kind of see it a little bit larger. Square root of x plus 1 is equal to -4. But go ahead and use inverses, solve the equation, all right? And then let's check it. Maybe we'll check it kind of on our calculators and see that the solution we get is false, and then we'll kind of really drill in and see why it's false. But take a moment to do that. All right, well, again, I've taken x, I've added 1, I've taken the square root, and I've gotten -4. So I'm going to undo that by squaring both sides and then subtracting 1, and we'll have it, right? So let's take this, square both sides. -4 times -4 is 16. I'll subtract 1 from both sides. And, doing everything that I did in the last problem, I end up getting 15. All seems like it's good in the world, right? I didn't do anything different than what I did in the last problem. And yet, if I kind of use my calculator, which for some reason we trust, right? If I use that calculator and I take 15 and I store it for x, and then I type out the equation, which is right here, square root of x plus 1 is equal to -4, it tells me false. Right? Even though every step I did was legitimate, it tells me false. So now let's actually do the substitution by hand and try to understand why it's false. All right, full screen. Here we go. So why is this false? Why is it what's called an extraneous solution? Well, if I go back to the original equation and I substitute 15 in, and let's say I do that kind of like, let me put a question mark there, right? I'll get the square root of 16 is equal to -4, but keep in mind, right, in this situation, the square root of 16 is only the positive square root of 16, right? It's not the negative square root of 16, and that's where students can, of course, get confused. But again, if square roots were always both a positive and a negative, our life would get way, way harder, right? In this case, it's basically saying the positive square root of x plus 1 is equal to -4. Now, for those savvy students, you can look at this immediately and say, there's no way this equation has any solutions, because the positive square root of x plus 1 can't be equal to a negative number. It just can't be, right, by definition. And in fact, when you do the check, you end up with something like this, which makes you go, well, that's obviously not true. Now, what really kind of gets us is that when we square that -4, it becomes positive 16. If the original equation had been root x plus 1 equals +4, then 15 would have been completely right because we would have had 4 equals 4. Or if we had negative square root of x plus 1 equals -4, then 15 would have also been a solution because we would have gotten -4 equals -4. But when we square, we kind of lose whether the number we're squaring is positive or negative because the result is always positive. We'll eventually be talking about irreversible operations in this course a bit, and one of the irreversible operations is squaring. Because once you square a number and you get a result, you don't know whether the number that you originally squared was positive or negative. So you lose a little bit of information in that operation. Okay, let's keep going. More complex equations. A more complicated scenario arises when a square root expression is equal to a linear expression. The next exercise will illustrate both the graphical and algebraic issues involved. Here we go. Exercise number 4. Consider the system of equations shown below. Y equals the square root of x plus 3 and y equals x plus 1. A. Solve this system graphically using the grid to the right. Awesome. Well, look, we've graphed square root equations, we've graphed linear equations. What I'd like you to do, and you can use your calculator to help you generate tables of values and things like that, but I want you to take a few minutes and accurately sketch y equals square root of x plus 3, accurately sketch y equals x plus 1, again, use tables if you need to or whatever, and then solve that system of equations by finding the intersection point or intersection points if there's more than one. Pause the video now and go ahead and do that. All right, well again, I'm not going to waste the time setting up tables and doing things that you would have been able to do back in Algebra 1, but I get these two graphs, right? I get the linear one, y equals x plus 1, which has a y-intercept of 1 and a slope of 1, so I get that nice sort of diagonal line. Then I get the square root function that's been shifted 3 units to the left, so I get that classic root function. And of course, what I find is that there is simply one point of intersection, and that's 1, 2. That's it, right? Or x equals 1, y equals 2. Either way, right? Right, or you don't need to have them both, right? Either 1, 2 or x equals 1, y equals 2. Either way. All right, now let's take a look at letter B. Solve this system algebraically for only the x values using substitution below. All right, so we know what the solution is. It should be x equals 1 if we're just solving for the x values, but let's solve it algebraically. Now, anytime we solve a system that is comprised of two functions, right, y equals and y equals, I'm just going to set those two functions equal to each other. So the first thing I'm going to do is do the square root of not x plus 1, but the square root of x plus 3 is equal to x plus 1. Now this is the first time you've solved an equation like this, and what I mean by that is an equation that involves a square root but also involves the variable x on the other side of the equation. Now to do this is not that hard, but the key really is we can't have the square root there anymore. Now since the square root is kind of all by itself, known as being isolated, what I'm going to do is I'm going to square both sides of this equation. Now, squaring this side of the equation is beautiful and easy because all that does is it undoes the square root. Those two cancel each other. This one, that's a little more complicated. That's x plus 1 times x plus 1. So if you need to, you might need to go to the side of your paper and write that down and kind of work it out. You know, do a little bit of foiling and stuff like that, and we get x squared plus 2x plus 1. Okay, now as soon as I have an equation that involves an x squared in it, I should start thinking about using the zero product law and factoring, okay? So I'd like you to pause the video right now. I'd like you to rearrange this equation so it's all equal to 0. Factor then the resulting expression, set each factor equal to 0, and solve for the values of x. Pause the video now and see what you get. All right, well, to get the zero product law to even apply, I'm going to subtract an x and a 3 from both sides. That's going to give me 0 is equal to x squared plus x minus 2. Right? I can now factor this trinomial by using product and sum considerations, and it ends up being x plus 2 times x minus 1. Right? Now that I've got it factored and equal to 0, I can set each factor equal to 0. X plus 2 is equal to 0, which means x equals negative 2. And x minus 1 is equal to 0, which gives me x equal to 1. Awesome. So I find that these two curves will intersect when x is equal to negative 2 and when x is equal to 1. Now normally, if I'm solving a system of equations, I should back substitute both of those into one of the two equations, probably the linear one, and get the y values. But this one said only for the x values. But let's take a look at letter C, because something's a little funny here. Letter C. Why does your answer from part A contradict what you found in part B? Well, take a look at part A, right, where we solved the system graphically, and then take a look at our answers in part B, and what is the inherent contradiction between the graphical way that we solved it and the algebraic way that we solved it? Well, it's very simple. Take a look. Here, there is but one intersection point when x is equal to 1. Here, there's two x values that solve it. X equals 1, which corresponds to this, and x equals negative 2, which has nothing to do with the y equals 2, by the way. Nothing at all. All right? So, you know, why does your answer from part B contradict what or part A contradict what you found in part B? In part A, there, wow, was only one x value, but in part B, there were two. All right, one of these is extraneous, and of course it's this one. We already know the correct one. It's x equals 1. All right, and that one would check and all would be good with the world. So why did we get that x equals negative 2? Well, we're going to devote an entire lesson to talking about extraneous roots, okay? But just to give you a little sense for it, you know, the reason it's really kind of happening is this thing, right, is half a parabola. It's half a parabola. If we kind of had the other half drawn in, it would look something like this, and there'd be another intersection point right there at x equals negative 2, y equals negative 1. The y value doesn't matter, but that would be that other negative 2. Now the thing is, though, that curve, right, remember this was y equals positive root x plus 3. This curve would be y equals negative root x plus 3. Right? Now, that's not part of our equation, right? We've got positive root x plus 3. But once we square it, whether we square positive root x plus 3 or negative root x plus 3, we still get just x plus 3. So in the squaring, we lose whether or not this thing was this upper curve or this lower curve, and therefore both of these two end up being a solution, right? But the only one that's truly a solution is x equals 1. So let's talk a little bit about, or a little bit more about extraneous roots. And the word extra is part of that because literally what an extraneous root is a value that shouldn't be there. It's extra. Sometimes roots are introduced by various algebraic techniques that for one reason or another are not valid solutions to the equations. These roots are known as extraneous and can always be found by checking within the original equation. So it's not like you're gonna get an answer and it will check and then your math teacher is gonna say, oh, nope, that's not right. But you can get an answer that is very legitimate in terms of, hey, I did all the correct algebraic steps, but when I take that value and I plug it back into the equation, it simply isn't correct. And that is an extraneous root. All right? So let's take a look at exercise number 5. Find the solution set of each of the following equations. Be sure to check your work and reject any extraneous roots. All right, so let's play around with exercise A, and then I'll probably have you work a little bit on B on your own. Anyway, let's take a look at A. Here we have the square root of 2x minus 3 is equal to x minus 3. Now, one of the nice things about this particular problem is that our square root is already what is known as isolated. It's all by itself. And if it's not, such as in exercise B, you'll want to get it all by itself. But right now, this one's all by itself. So the first thing I'm going to do is I'm going to rewrite the problem down just so that we can see it a little bit better. All right. And then what I'm going to do is I'm going to square both sides. The reason I'm going to do that is that squaring a square root gets rid of it. Now, this one I have to do a little bit more work on, right? So off to the side of my paper, I do a little x minus 3 times x minus 3, and I get x squared minus 6x plus 9. Okay. And then I go into zero product property, right? I got to get everything equal to 0. I have to factor and solve. So I'd like you to pause the video right now and go ahead and see if you can find the solutions. And once you have them, then check them in the original equation. Now, you got a handy dandy graphing calculator that can make that check awfully easy. So pause the video now and see what you get. Okay, so let me subtract a 2x and add 3 to both sides. All right, just to kind of get everything out of the way and equal to 0. I'll get x squared minus 8x plus 12. All right. If I factor that using product and sum considerations, I'm looking for two numbers whose product is positive 12 and whose sum is negative 8. Those happen to be x minus 2 and x minus 6, right? Then I'll take x minus 2, set it equal to 0, and get x equals 2. And then I'll do x minus 6 is equal to 0 and get x equals 6. Both of which look like very legitimate roots, right? X equals 2, x equals 6. Let's see what the calculator thinks. So without doing the check by hand, what I'm going to do is I know that my two solutions were, and let me clear this all out. There we go. Let's take a look at the 2. I'm going to take 2, I'm going to store it in x. Nope, okay, let's try that again. Escape. Try one more time to store it in x. There it is. All right, I'm going to put in, I'm going to put in square root of 2x minus 3. Nope. I'm having a real hard time right now checking this. Would have been probably faster to do it by hand. Here we go. The square root of 2x minus 3 is equal to x minus 3. And it says false. So it appears that x equals 2 is extraneous. And we'll take a look at checking it by hand to see why that is in a moment. Let's take a look at 6. Believe it or not, they could both be extraneous. They can be. Or they could both be valid. Isn't that a bummer? All right, so I'm going to do 6, and I'm going to store that in x. Now, one of the beautiful things is I can just go back up until I get to my equation, hit enter, and now it's true. So it appears that x equals 2 is an extraneous root because it's making my equation false when I substitute it in. And x equals 6 is a valid root, a valid solution, because it's making it true. How wonderful is that, right? I mean, there it is. So I can definitely circle this one and put a line through that one. But real quick, let's do the check by hand on x equals 2 just to show why it is, in fact, an extraneous root. So if I just do this check by hand, right, I would have the square root of 2 times 2 minus 3 is equal to 2 minus 3. All right, here I would have 2 times 2, which is 4, minus 3 under the square root is equal to negative 1. Here I'd have the square root of 1 is equal to negative 1, and 1 is equal to negative 1. Nope. Right? Not true. And again, what's really kind of coming up is that fundamental issue, that issue of, hey, the square root of 1 is both 1 and negative 1, but this is only the positive square root of 1, right? It's only the positive square root of 1. And if I took 6 and I substituted it in, eventually what I'd get is something like 3 equals 3. And I'd say, okay, great, 3 is equal to 3, and that's a correct solution. Let's take a look at b, which is definitely more complicated. 2x is equal to negative square root of x plus 6 minus 2. Now, one of the problems with this particular one right away is that we've got this negative 2 hanging out with our square root expression. We want to isolate the square root. We want to get it as alone as we possibly can. So even though I want you to work on this one on your own, the first step, let's do together. So what I'm going to do is I'm going to add 2 to both sides, and I'm going to get 2x plus 2 is equal to negative root x plus 6. Now, if you really wanted to, you could certainly divide both sides by a negative 1 and eliminate that negative, but you don't really need to do that at this point, okay? At this point, you can square both sides, because when I square that negative square root, I'm still going to just get the x plus 6. Doesn't matter whether there's a negative or a positive there. A negative times a negative is a positive, and that square root will kind of go away. So see if you can work through the rest of the algebra here. All right, well again, somewhere on the side of your paper, right, you're going to be doing a little 2x plus 2 times 2x plus 2. That would be 4x squared plus 8x plus 4. Gosh, looks like plus 14. Anyway, so we're going to get 4x squared plus 8x plus 4 is equal to x plus 6. Kind of want to use some zero product law, so I'm going to subtract x and subtract 6 from both sides. That's going to give me 4x squared plus 7x minus 2 is equal to 0. And now this is one of the harder factoring ones, right? Here we're factoring where a leading coefficient is not equal to 1. So let's kind of review that process, right? I might be looking at this and using what's called the AC method of factoring. So I'm looking for two numbers whose product is negative 8 and whose sum is positive 7. And those end up being positive 8 and negative 1. So I will now take my 7x and break it up into an 8x and negative x. Okay, I can now do factoring by grouping. Put a little plus there. I'll pull a 4x out of here and I'll be left with x plus 2. I'll pull a negative 1 out of here and also be left with x plus 2. So I can then factor that as x plus 2 times 4x minus 1. And that will leave me with x plus 2 is equal to 0, and x is equal to negative 2. 4x minus 1 is equal to 0, which means 4x is equal to 1, and x is equal to 1/4. Now that's a lot of work to get two answers, which possibly both could be extraneous, or both could be fine, right? And of course, checking, especially with the 1/4, gets to be very complicated, right? So you want to take both of those probably and use your calculator to check. Let's check the harder one. Let's check the 1/4 really quick. All right. So if we take 1/4 and we store it in x, now it might be helpful to go back and see what our original equation is. There's our original equation. So now we're going to type in 2x is equal to, always use the original equation. Don't use any transformed part of it. Otherwise, you could be checking something that's already has a mistake in it, right? So I've stored 1/4 in for x. I've typed out my equation. I hit enter, and it's false, right? What was my other answer? My other answer was -2. Let's check that one, right? So I'll do negative, maybe they're both extraneous. -2, store it in x. Go up a little bit until we get to that equation, and that one's true. All right, so we know the 1/4 in this case is extraneous, the -2 is fine. So we're going to go back in, come all the way down here, draw a line through that, circle that, and we're done. All right, let's wrap this up. So today was probably the first time you've ever solved an equation that has a square root in it. And ultimately, if an equation has a square root in it, and there's an x underneath that square root in some way, but there's no x's anywhere else, you can typically solve those equations by just simply undoing what's been done to x, and especially the important thing is that squaring is the inverse of that square root, right? Now, most of those types of equations don't involve extraneous roots, although we did see one in that first exercise where we had an extraneous root, right? Where we had the square root of x plus 1 is equal to -4. So you do want to be concerned about extraneous roots anytime you end up squaring a negative. That's really the hallmark of it, right? Now, the more challenging square root equations are when one side of the equation has a square root in it that involves an x, and the other side of an equation also has an x in it, right? In those situations, what we always want to do is isolate the expression that's got the square root in it, right? Moving everything else to the other side. Squaring, which will often take some side work, especially because you tend to be squaring a binomial. Then, tendency after that is to have an equation that involves an x squared in it, a quadratic equation. Those we're typically going to solve by using the zero product law, getting everything equal to 0, factoring, setting each factor equal to 0, and it's almost always the case in those situations that an extraneous root will occur. If you've got that graphing calculator with the store command on it, it is exceptionally easy then to tell whether or not you actually have a legitimate solution or not. So please, whether you're checking by hand or whether you're using the store feature on your calculator, make sure to check your solutions and reject anything that's extraneous. All right, well, these equations will come up a little bit as we move through the course. And again, we will take a look at extraneous roots one more time and why they truly occur. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.